Thank you, Abbas and Molly. It's great to be here with you today. I've helped to put together this workshop to some degree, although Molly and Abbas have done most of the work. So when we put together the list of speakers and the topics, we were, in a sense, focused on the southern mid-continent, which in my mind includes 6 states: Arkansas, Kansas, Louisiana, New Mexico, Oklahoma, and Texas, only because those are the states that we've worked with on regional induced seismicity issues and produced water management issues. And so my talk today will be focused mostly on the southern mid-continent, and I'll pay most of my attention to Oklahoma, a little bit of attention given to Arkansas as well. But we have other speakers lined up for the neighboring states, so hopefully I won't cover too much of their material in this presentation. So I want to start broadly with produced water quality information in the US that's available, looking at the USGS produced waters geochemical database. So I think in the introduction, Abbas hinted to the fact that I've been working on produced water, saltwater disposal, produced water quality in Oklahoma for several years. I've been at the OGS for 10 years now, and we've been working on this topic for quite a while. Part of the motivation to get into the critical minerals arena was from the idea that we needed to reduce our disposal volumes in Oklahoma, and that entailed treating produced water to minimize or reduce the disposal volumes. In the process of treating it, it's important to understand what's in the water. So I began to study the produced water quality so that we could design effective treatment methods. And so when I began working on this topic, the data that were available for produced water quality were mainly from the USGS produced waters geochemical database. I think it's in version 2.3 now, which might be several versions old. But what you see on this map is that most of the data in this database is from conventional hydrocarbon reservoirs. So you see the symbol here is the open white circle is conventional hydrocarbon reservoirs. So in the southern mid-continent in Oklahoma, and generally in this area, you see only a few samples from unconventionals. So most of the data that we have to work with for Oklahoma, and I think you could see from Texas and Louisiana and neighboring states like Kansas, it's almost entirely conventional hydrocarbon production. So it's actually several decades old, the data that we have access to. So I'll show you a quick analysis of data from this database, but then focus more on produced water quality data that I've put together for Oklahoma in an ongoing effort to understand produced water production, water quality, water treatment, and then potential to recover critical minerals and other elements. So the other speakers have talked about critical minerals and defined them. I've included a definition here for critical minerals: elements that are critical to the US economic and national security because they have important uses, no viable substitutes, and face potential disruption in supply. And I've highlighted on the periodic table 54 critical minerals. And that number might vary depending on what document you look at and who you talk to, but those are the ones that I've identified from the literature. I also have highlighted what I call industrial minerals that are naturally occurring elements that have some economic value. And I've included those because Oklahoma at least has some production of industrial minerals presently. And we are I believe, the sole source of iodine production in the country. And it comes from brine or produced water in the oil and gas field. So what's interesting about the critical minerals and elements that I'm looking at today and presenting today is that the ones that we have the most data for in brine or produced water tend to be in the class 1A and 2A groups because they're ionic. So we can measure those concentrations fairly easily. And then we have the anions in the 7A group. So I'll spend a lot of time looking at some of those concentrations. And my presentation is a little bit data intensive. So you have to get comfortable looking at the graphs and trying to interpret what I'm showing you, and then make use of the information. And I'll try to walk you through what I've done so far. So starting with this first graph, this is an illustration of the commodity value for the critical minerals or industrial elements that were on the previous list. So I remember I had 54 critical minerals and 9 industrial minerals. On this slide, I'm showing 51 critical minerals or industrial minerals that had a commodity value available in the USGS National Minerals Information Center website. Some of them are actually off the scale here on the low side because they had values of less than 1 cent per kilogram. So you can see very high value critical minerals and elements, including rhodium, scandium, palladium, iridium, platinum, rubidium, ruthenium, and so on, cesium. So some of those are more than $1,000 per kilogram, more than $10,000 per kilogram, and more than $100,000 per kilogram, which is really hard to believe. What that tells me is that if we have concentrations of those elements in produced water or brines, concentrations don't need to be very high before it's economic or potentially of economic interest to extract those elements from the produced water. Some of the others of note here, iodine in this range, I think it's about $16 per kilogram presently, and we're producing that in Oklahoma. Bromine or bromide, boron, cadmium, and of course lithium, our most popular famous critical mineral, which is just less than $10 per kilogram. So I'm going to use the commodity value and the concentrations that I've been able to compile for produced water and brines from the USGS database and the Oklahoma database that I've compiled myself to present to you kind of a dollar per barrel rate that we might be able to put together for these elements. So we could look at the importance of brine or produced water versus solids with this simple chart on the left, or table on the left. You see an example for lithium resources worldwide, and some of the highest concentrations and the largest resources that are available are actually coming or potentially available in brines. So Bolivia has the greatest resource available, and it's a brine with a pretty low concentration of lithium. If we look at some of the US resources, pegmatite for lithium, I think someone mentioned that earlier, the Kings Mountain area, North Carolina. And then we have the United States, more brines in this area. Concentration is not noted for the Brawley. We have US brines in Western US, in the Silver Peak and Salton Sea, concentrations in percent, 0.02% lithium. So we could take some of this information in percentages or concentrations and the commodity value in dollars per kilogram and do some math and try to understand the approximate value of that resource, given that we have concentration or percentage, and we also have a total resource value. But if we zoom in on the US and we look for potential brine resources in the Midcontinent, obviously one that we're going to hear more about, hopefully from the Arkansas speakers, is the Smackover, which is in southern Arkansas, northern Louisiana. And I have a little bit of data on the Smackover that kind of carries into this presentation. So I want to spend a lot of time on this particular chart because I've taken a lot of time to put it together and try to illustrate how you might approach prospecting for critical minerals or industrial minerals and elements in brine. So what I've done is taken the 51 critical minerals or industrial minerals that I had commodity values for from the USGS site. And then I've gone through the USGS produced water geochemical database and looked for concentrations of those elements in the southern Midcontinent, specifically Oklahoma and Arkansas. And what I ended up with were 21 critical minerals or industrial minerals that had concentrations in the southern Midcontinent. I selected 9 of those that were of interest to me in this presentation today. And so you see, what you see here are 2 symbols. The first one, if it's a circle, it represents the mean concentration of that element in produced water in Oklahoma. And if it's a triangle, it's the mean concentration of that element in produced water in Arkansas. And it's maybe a little bit biased. If you look at the geochemical database for the US from the USGS, most of the produced water samples in Arkansas are in southern Arkansas. So they are close to that Smackover resource, and they're probably skewed to the high end. So you couldn't drill a well in northeastern Arkansas and expect to get the same concentrations. This would be representative of the Smackover for the most part. Whereas the circles are representative of the entire state of Oklahoma. And again, they're conventional reservoirs or conventional resources that we're looking at. So we don't have a lot of information in that database on the Woodford, for example, or the Hunton Group, or even the Mississippi Lime Formation in some cases. We're missing some information there. So it's usually shallower, more conventional type resources. So you see those symbols, Oklahoma concentrations, Arkansas concentrations, and I have noted aligning with the y-axis is the value or commodity value in dollars per kilogram. So rubidium is worth, if you do the math, $16,080 per kilogram if you can produce it from a brine. Cesium would be $2,100 per kilogram. And we move down to some other critical minerals like barium, which is only 18 cents per kilogram, and boron at 38 cents per kilogram. So how do we use this chart? Well, what we can do is quickly assess kind of the viability or the economic viability of producing and extracting these elements from brine. I've added 3 lines to this, dashed lines to this chart to help illustrate that. So you see the red line, red dashed line represents the $1 per barrel value. So if we extracted, let's say, got my laser pointer here, if we extracted cesium from the average well in Oklahoma, with an average concentration of about 0.5 parts per million, we could expect to have $1 per barrel value of cesium. Whereas in Arkansas, the value would be about a 10-fold higher. We would see about, I'm struggling because the Zoom bar is covering my slide. Okay. So we would have about $2.50 per barrel value. I'm sorry, we would be between $1 per barrel and $10 per barrel. So we would be closer to about $8 per barrel because the concentration is higher at 2.5 parts per million. So we could continue to look at this chart to understand the potential value and the range of variability in those elements. So let's look at iodine, for example. In Oklahoma, the mean concentration that I have from the Oklahoma Produced Waters database is 100 parts per million. And so we would have between $1 and $10 per barrel, close to $5 or $6 per barrel if we extracted at that concentration. In reality, I know that if you sample in the area where iodine is currently produced, the concentration is higher. It's closer to 300 parts per million. So in western Oklahoma, where iodine production is currently occurring, we're getting about $10 per barrel value out of those wells. And so you can see several of these critical minerals or elements, industrial elements, are in the $1 to $100 per barrel range. So it seems like they could be attractive options if you're already handling produced water and you can marry the produced water treatment process with critical mineral or industrial element extraction, then you can offset the cost of that produced water treatment by selling that commodity. It doesn't seem like it would be super appealing to go after some of the lower value products because their concentrations just aren't high enough in that raw produced water. We'll return to this chart with some more specific data for Oklahoma. So in Oklahoma, we have in the last decade or more, about 10 to 12 years, we've seen increased volumes of produced water. One of my objectives was to understand what formations, what zones was that produced water coming from. So I spent a lot of time looking at water to oil ratios, water to gas ratios, oil and gas production rates, and tried to estimate the zones from which the produced water was being generated in Oklahoma. You see in map view, a relative production rate of produced water that I've estimated, with the dark colors indicating higher produced water volume generation. So Woods County, Alfalfa County, Oklahoma County, which is right below Oklahoma City, Lincoln County and Seminole County, very high produced waters are being generated there, high volumes or high rates. And in the chart on the bottom, you see color-coded to match the stratigraphic column, the zone from which produced water is generated. So the dark blue color corresponds to produced water coming from the Mississippian aged rock. And the yellow color corresponds to produced water being generated from the Devonian to Middle Ordovician. So if you look at this snapshot of, or estimate of produced water generated in Oklahoma, clearly the large majority is coming from Mississippian and the Devonian to Middle Ordovician age rock. So if we want to understand the potential for resource recovery or critical minerals extraction from produced water, we're going to be dealing mostly with waters from those two formations. So the first representation of the dollar per barrel versus mean concentration was from the USGS produced water database, which, as I stated, mainly represents conventional resources or conventional reservoirs. So those produced water samples, although they're valuable or useful for us, they're not representative of our current situation in Oklahoma. Fortunately, in collaboration with the Oklahoma Corporation Commission, I learned a few years ago that there are when an operator applies for an underground injection control permit with the Oklahoma Corporation Commission, or OCC, they are required to submit a representative sample of produced water that would be injected into that well. So it could be a saltwater disposal well that they're permitting, or an enhanced oil recovery injection well that they're permitting. And so in theory, there's about 15,000 UIC wells active in Oklahoma. Most of those are enhanced oil recovery injection wells. About 3,500 of them are saltwater disposal wells. So in theory, each one of those wells that were permitted should have a quantitative analysis of a representative sample of water to be injected. And that usually means that total dissolved solids, chloride, and sodium are reported. But fortunately, sometimes operators want to know more about the water than those three minimums requirements, and they will analyze for some critical minerals. Specifically, lithium is commonly included. So I've been in the process for the last few years of putting that information into a database for Oklahoma and trying to, at this point, starting to analyze the data and make sense out of it and understand the availability of things like critical minerals in Oklahoma for extraction from produced water. This slide shows the current status of the database. I have about 1,500 samples that I've compiled thus far, and they are color-coded like the stratigraphic column that you see on the right. So some of the ones in the northern part of the state, in Mississippian Play, you can see we have produced water samples from the Mississippian. In the central part of the state, you see that yellow color, Devonian to Middle Ordovician samples. And in other regions like west of the stack, for example, you see some younger produced water samples or shallower zones. And you might see some Woodford samples in other locations. There are a lot of the orange color, which means I can't tell you exactly which well that came from or which zone it came from. So it's other, I put it into the other or unspecified category. So what I'm doing with this data is basically looking at the produced water quality in the bulk form and total dissolved solids concentration, and then starting to look at critical minerals and other elements of interest in those produced waters. So a little bit data intensive here. I think one of the good things about Zoom is that you can actually see some of these slides at this scale if you're sitting in front of your computer. So what we have on these slides, just to go through them pretty quickly, is on all of them, I have a box plot that shows the inner 50 percentile. So the 25th percentile is represented at the far left of the box plot. The median is where the color changes from light green to dark green. And the 75th percentile is on the right side of that dark green bar. And then of course the min and max is at the end of the whiskers. Sometimes the end is not on the scale. What you have on the x-axis is the concentration in parts per million. And on the y-axis, the producing zone that I've put together from the stratigraphic column on the previous slide. So the total dissolved solids concentration is always reported. I want to say always reported. I have 1,566 samples of those. The largest zone that's reported is Mississippian. So we have produced water quality, a lot of TDS concentrations from the Mississippian. and the median is close to 200,000 parts per million. So very salty water coming from the Mississippian. The second unit that produced a lot of water, according to my calculations previously, is the Devonian to Middle Ordovician. Again, on the high end of the salinity or TDS scale, with maybe 170,000 parts per million is a TDS concentration. So that kind of sets the stage for what we're dealing with. The zones that produce the most water produce the saltiest water. If they produce salty water, it's pretty likely that they would have some of the critical minerals and industrial elements also dissolved in that water. Generally, higher TDS waters in Oklahoma have a lower pH, which I would say lends to them being able to dissolve more elements. So just to barrel through some of these charts, you see barium concentrations on the upper right. And this scale is different, of course, 0.1 parts per million up to 1,000 parts per million. And if you look quickly, you might say, well, the highest barium concentrations are coming from the Devonian age rock. That's the median, which is close to about 80 parts per million. The Devonian happens to coincide with the zone that Abbas showed earlier with a lot of coal layers. So I don't know if barium has anything to do with the abundance of coals in the Devonian age rocks, but it's something to think about. If we look at boron in the lower left, we could see that the Mississippian has the highest concentrations of boron. Bromine in the lower right, we don't have a lot of data for bromine, but Mississippian is the one with the most data, and it has the highest TDS, or highest bromine concentrations. You can see I put a map in for bromine because I've gotten a lot of questions about it. Most of the bromine samples, maybe hard to see, but they're in northern Oklahoma, and I've included some in Kansas because of the data collection effort that went on in this area. Some of the data were provided by operators, so they're recent and of interest to our local operators. And then the second group of charts, we're looking at a few other elements. We have copper, not very much data for copper. I think we have, 21 samples total. You see in the upper left, most of those are from the Mississippian. The median concentration is less than 0.1 part per million. Iodine concentrations, not a lot of data in my database, but obviously there's iodine production in Oklahoma, and we know a little bit about that. We have previous OGS publications on iodine. Mississippian, according to this database, has the highest concentrations, but most of the production comes out of the Moro Formation in western Oklahoma. And I included on this chart in miniature form a table that shows the halogens in Oklahoma versus brine versus seawater versus organics that seem to concentrate some of the halides. So chloride, bromide, and iodide are shown here. And the mechanism by which iodine is concentrated is seems to be consistent with organic material in a marine environment. Seaweed, coral, organisms that concentrate iodide are probably the source of iodine in our subsurface waters. Then we have lithium in the lower left corner. We have 90 samples thus far for Oklahoma and some in Kansas included. Mississippian lithium concentrations in Oklahoma, the median is about 10 parts per million, not super high. And then magnesium, which you may not have thought about as a critical mineral, but we have high magnesium concentrations, and we have lots of data for magnesium since it's pretty commonly analyzed as a major constituent. It looks like the Missourian age rock has the highest concentration of magnesium. So what can we do with these data? We can go back to my chart and plot some of the information and look at the variability in space, in time, by zone, and try to understand how we might use this chart to strategize for prospecting purposes. So we have the barium concentration, median concentration. If we added that to our chart, trying to draw things quickly here. Barium, the concentration is about 80, so it doesn't move the needle much here. If we use this new data set. Boron, we have a median concentration of 70, so this is for Oklahoma, so that moves the needle a little bit, moves us still into this range, still in the low value range. Bromine, 724 in the Des Moines, so that does move us up the scale. So we're up in the $2 to $3 or $4 per barrel range. How about copper? Des Moines is our zone with the highest concentration. It's 0.8. And so that doesn't help us a whole lot. That actually moves us down the scale. We're down here now. Iodine, 329. So as I told you earlier, this is the mean concentration from all of Oklahoma. But if we look at the Woodward Trench area where we're actually producing iodine, we're up in this range. So we're looking at about $10 per barrel value. Woodford is the highest for lithium. There was only one sample of that one, I think. 16 parts per million in Oklahoma. So it doesn't move the needle much, moves us up to here. And then magnesium, 2092. That would move us up a little bit, but we're still lagging behind the magnesium concentrations in the Smackover, but we're above the $10 per barrel line. So just to give you some idea of how this kind of chart is useful to evaluate the potential to recover some of these elements from produced water. I included also a chart that shows the commodity value over time, because my y-axis on the main chart is the dollar per kilogram value in 2020. Some of those values change dramatically from one year to the next. So I have bromine here as an example in green. That's pretty steady. We have lithium in this kind of bluish color. That's not very steady. It changes quite a bit from $6 per kilogram to about $17 per kilogram. And in 2020, it was $8 per kilogram. So you can see a lot of variability there. That would mean that if we want to use this over time, we would have to have kind of an error bar in the y direction as well.
Kyle, could you wrap up in about 2 minutes?
Yes.
Thank you.
My error bar is a little bit larger or longer than it is in reality. So moving on to the next slide. Just to wrap up, I have a few slides on treatment. The idea is that produced water treatment, in effect, when we wanted to reduce our disposal volumes in Oklahoma, we probably needed to do some desalination. So we're going to take produced water and flow back water. We're going to run it through a desalination process of some sort, some degree, and we're going to end up with a concentrate. That concentrate is now enriched in critical minerals and recoverable elements. Some of the processes that you might see in the oil and gas field result in some of the critical minerals and recoverable elements being concentrated. And they pair nicely with recovery of those elements. A couple more examples where we have RO concentrate for iodide recovery. We have a bromine operation here by a company by the name of Standard Lithium. So obviously lithium and bromide are co-located in this particular operation. I included a few things on naturally occurring radioactive material because as a water person and being environmentally minded, think it's important to recognize that if we concentrate these elements into a brine as we treat it, we're also concentrating some of the bad guys too. So radium is the most common radioactive element in produced water. So if we treat water, we're also concentrating norm. And I have here the maximum contaminant level for radium, total radium, which you can see clearly from this chart. In produced water, it's already well above that maximum contaminant level. So if we concentrate it further, we're going to be concentrating this radioactivity as well. So something to keep in mind as you deal with produced water and you try to recover critical minerals or elements, you're going to be trading one problem for another potentially. Okay, so just one final slide. Some of my closing thoughts. There are numerous critical and industrial minerals in produced water and brine, and they are at concentrations that have the potential for resource recovery. I've spent a lot of time on data collection and compilation, but there's still a lot of work to be done there. And I really haven't dug into the research on why are some of these elements enriched in one area versus another. I think there's some work that needs to be done to try to understand how we can actually do a good job of finding high concentrations of these elements. And then pairing with produced water treatment processes, obviously we can have an economy of scale if we put those treatment processes together with resource recovery, but we also have the potential for harmful radioactive materials. And I'll end there. I saw a bunch of chats coming in, but I'll let Molly or Abbas guide us through those. Thank you.